Okay, so we've talked about all the pieces of a hash table. We've talked about how to avoid collisions using chaining and linear probing, but another factor that influences hash table design and whether collisions occur or not are, of course, the design of the hash functions themselves. And hash functions have long been a topic of great interest in a lot of settings. And entire PhD theses have been written on hash functions. So this is a deep topic in which I'm only scratching the surface here. The good news is there are a lot of well-known hash functions we can just use. We don't need to reinvent them ourselves, but it's worth talking a little bit about what they are, how they work. Okay, so an ideal hash function, or a perfect hash function would spread keys uniformly across all buckets, magically avoiding collisions. Right, somehow, right, if I have a length 100 hash table and I had 100 items to insert, then that hash function would just perfectly spread the items across all 100 entries without there ever being a collision, right? That's the ideal scenario. Some sort of oracular knowledge could allow you to do that. But in the real world, we don't have ideal hash functions. So we settle for heuristics that work well on the average case. You run the program, you count how many collisions happen, and you figure out, oh, some hash functions work better than others, and we pick the ones that work better. The simplest kind of hash function is a modulo hash function. So a modulo hash function uses a remainder after moduloing by the size of the table. And this works for integers really well, and it forces indices to be in the proper range, right? Because whatever my key is, assuming it's an integer to start with, if I modulo it by the size, then index has to be in the range of 0 to size -1. There's no other value it can be. And so that forces it to be a valid index. And this seems good at first, right? Because it at least solves the problem of how do I get an index in range? But it can cause problems if the keys share some sort of systematic relationship. Like what if my keys are all multiples of 100, 100, 200, 300? It could happen. So what's going to happen if I mod by 100 is that I'm going to get 0 for all of my indices in my hash table, and that's clearly not good. So one thing you can do to kind of avoid some issues like this is you can make the size of the table a prime number. And since prime numbers, tend to be a little more rare, you don't tend to see as many systematic relationships on prime numbers as you do on like multiples of 10 or powers of 2, then, that may solve some of this issue. Okay, but it doesn't solve the whole thing. So we can come up with a more sophisticated function for scrambling integers into kind of a random set of values. And so one such hash function is called the mid-square integer hash function. And the idea is that rather than just taking the whole integer value and moduloing it, we kind of scramble the bits a little bit. And the way we scramble the bits is first we take the key, right? And so I'm just showing you here like 24 converted into binary. And then we multiply the key times itself. And so that produces a new bit pattern. And then we just pull out some of the middle bits from that number. Rather than taking all the bits, we kind of randomly just pull out some of the bits. And so when we do that, we get the number 36, and then we mod 36 by 10, and that gives us the number 6, right? Assuming this mod 10 it says that we have a length 10 table. And if you try this with a bunch of different numbers, you'll see that it scrambles the number we're starting with in kind of a somewhat random way. And it helps us avoid some systematic dependence on being a multiple of the modulo. There are some tricks when you extract the middle bits. You want to make sure that the number of bits you extract is much, that the number of bits you extract is large enough to really spread the whole table. Otherwise, that when you extract these bits, your range of data will be too small and you'll have done yourself a big disservice, right? You won't be able to generate values across the whole range of the table. So there is a little trick here. You need to satisfy this rule. Now there are a lot of other integer hash functions out there. This is not the only one. I'm just using this as an example of taking some integer and performing some math on it. There will always, the key here is that whatever you do, whatever math you do, the number you start with you need to systematically convert it into a new number so that anytime you give it 24, you get some new value, which you then can modulo. It can't be a function with memory, or it can't be a function that adapts and tries to pick a new index every time. Because then you can't reliably know where you stuck the data in the hash table, right? So it just has to be some sort of proper one-to-one function. As long as it does that, then you can use it as a hash function. Another thing we commonly put in hash tables are strings. And the reason for that is kind of obvious, right? We often want to search for strings. And we often want to, store sets with strings in them, right? Whether it be a set of names or a set of variables, or a set of websites, or whatever it is, a set of search terms. We just often need to search strings. And so having a hash function for strings is important. Now the problem is we want the hash index to reflect the value of the string, so that if I've already stored the same string in my hash table, I detect that. So we can't just use the address of the string or something like that. We need to incorporate the whole value. And then another problem is that strings can have varying length. And so we need to take into account the varying length of the string and the actual content of the string in order to calculate our hash index. And one really popular string hash function I'm showing here, called DJB2, does all those things. So first we start with like a random integer value. And then we loop over the string some fixed number of characters. And we add in the value of that position in the string into the current value, and we multiply the current value by some factor like 33, some somewhat prime number. Actually, this might be better if it's 39, but and you just sum up all the character values in the string. Okay, and then at the very end, we modulo by the size of the hash table. Now this formula is weird. It doesn't really have any meaning, but the only thing it's doing is it's taking the content of the first 10 characters of a string and adding them together. And so as it does that, it's kind of shifting over. This multiply times 33 is kind of like doing a shift, right? So that each character is setting different bits of the number. And so this is going to give you an approximate representation of the content of the string. And so two strings that are different will produce different numbers. Two strings that are the same will produce the same index, the same number. And so that will let us, that'll help us guarantee that if I've already put a string into my hash table and I want to put the same string again, I'll calculate the same index and I'll go look in the same place. And this guarantees I generate a lot of indices, right? A lot of different indices kind of randomly based on whatever happens to be in the string. I'd encourage you to take this code, run it, and look at some of the values it produces. Okay, so that's integers and strings. Those are common primitive types we want to hash, but what about other kinds of objects, right? The whole purpose of C++ is we want to be able to make any kind of object and then use those objects, in a set if we want. So what about hashing other types of objects? Well, we can certainly do that. We just have to come up with a way to hash the object's key to an index. And the hashing would depend on the details of, whatever that object is. So let's think back to that historical dates object that we had. What we could do is hash together the day, month, and year into some value. Like I could take the year, multiply it times 4,000, then add the month times 100, then add the day. And this is going to do a pretty good job of creating a unique number for a given date, a given point in time. Now, it doesn't include that significance string that tells us what the day is about. So what I could do is use that hash table from the previous slide to turn a string into a number, and then I could add that number into this date. And then that would produce a really unique number that represents that historical time. Now, is it possible that two different historical dates would somehow map to the exact same index? Yeah, it's possible. That would be a collision, and we could deal with that collision in some way. But, we have to think about what's in the object and then come up with a way of writing a hash function for it. It's not something we can easily do automatically, but it's something that if we think about the object, we can do. Now, can we hash all kinds of objects? Well, there's really no systematic way of doing this. Like, we can't ask the compiler to do it for us because it just doesn't know enough about what an object means. The designer of the object has to figure it out. And truthfully, sometimes it is impractical. Like, what if your object represents a whole database? Then it would be impractical to produce a hash index based on the contents of an entire database. Or even let's take something simpler. Let's say a linked list. Then the key would need to simultaneously account for all the data in the list, the order of the data, and the size of the list. And that gets pretty cumbersome to do. And maybe just not worth the time of a programmer to figure out what that hash function should be and whether it's going to work well in some context. Okay, so it's not always so simple. You know, primitive types, integers, strings, we can do very easily. Complex objects, sometimes we can do, sometimes we can't. If there's no easy, obvious way to write a hash function for a complicated object, then there is kind of a simple fallback plan. And that fallback plan is that we can just use the address of the object as the key. In other words, you know, the location of an object in memory is always unique because that object is given a dedicated part of memory. And so its address is a unique key. And so pointers can be treated as integers and we can just hash them. And so we can use the address of an object, treat it as an integer to make a hash function for arbitrary objects. Okay, now this does have some implications that we need to be aware of. This implies the hash table is tracking a set of unique objects, okay? And this is often effective for really exotic kinds of objects. However, addresses don't really tell us what's in an object. So that means two different objects could actually hold the same data and we wouldn't realize it when we use their address. Let me give you an example. Let's look at the difference between hashing a pointer versus an object for the case of a string. Okay, so let's say I have three objects, S1 that holds the string A, S2 that holds the string B, and S3 that holds the string A again. And then I have two different key types for my hash table, one that's a string pointer and one that's just a string. So for string pointer, I'm only gonna look at the address of the object, but for string, I'm gonna look at the content of the object. Okay, so for string pointer, if I insert S1, then I'll have a set with the address of S1 in it. If I insert S2, I'll have a set with the address of S1 and the address of S2. And if I insert S3, I'll have a set with the address of S1, S2, and S3. So I have three objects in my hash table if my key is the address of a string. But if my key is the string itself, when I insert S1, I'll have the string A. When I insert S2, I'll have the string A and B. And when I insert S3, I'll still only have A and B because I'll realize that S3 holds the same thing that S1 holds, and I won't add it to my set again. So the behavior I get is very different depending on this key. And so you should be aware of this. If you decide to hash based on address, then you will insert all unique objects into your hash table, but those objects may in fact have the same data in them, which looks a little more like a multi-set than a set, right? But this may still be okay for some, you know, for whatever the purpose is you have in your program for, you know, wanting a set. It's just something you need to keep in mind, that hashing a pointer is a little different than hashing an object itself. Okay, so hash functions must be adapted to the type of key being hashed. So integers and strings and any other kind of object, they all need their own specialized hash function. Over the years, integers and strings have received a lot of attention. So there are really good hash functions you can just use for those. A complex object that you implement can also be hashed using a key, but you have to come up with it possibly and write your own kind of hash function for it. If you don't want to write a hash function, you could just use its address as the key. But this implies that all you really care about is a set of unique objects, not necessarily a set of unique values.